Alright, let's take a look at our last condition or last rule for what happens when I put conductors in an external electric field. And the last condition is this, that I have a conductor, and in that conductor we have a cavity. So there is a conductor surrounding a hollow space, and I apply an external electric field. The question which comes is, what happens to the electric field inside the cavity, and what happens to the charge which is created on the surface? Is there any charge created on this cavity surface? Let us try to understand this in a very physical way. And the way I'm trying to explain it to you was first explained by Richard Feynman in his physics notes, in the lecture he taught in Caltech for introductory physics. So we have this external electric field. We already know that there must be some electrons which would start gathering on the surface. So the question which comes now is, are these electrons coming from the cavity surface here, or are they coming from somewhere else? Are these electrons just going to come from this part of the surface, leaving a positive charge there, or are they going to come in another part of the surface? Let's try to answer that question. So let's see. Again, we have a conductor and a cavity inside the conductor. Let's, for the time being, assume that the electrons which have gathered from the surface. Now, if I apply Gauss law, so I'm making some arbitrary Gaussian surface. It's a closed surface, so I can apply Gauss law. If I apply Gauss law on that surface, well, E inside a conductor, we have already concluded in a rule 1, E has to be 0, and that rule cannot be broken. So when I calculate the flux has to be 0, which tells me that the net charge within that has to be 0. Gauss law does not preclude the fact that there could be positive charges on this part of the surface, but Gauss law guarantees you this, that if there are positive charges on this side of the surface, there must be an equal number of negative charges on the other surface, and thus there should be some positive charges on the back surface. To make sure Gauss law is true, if I am putting a positive charge here, then there must be a negative charge somewhere, and most probably on the other side of the surface. What would this lead to? Well, if we are saying that I have this cavity, we are saying that there is some positive charges which have collected here and negative charges which have collected on the back side, then there must be an electric field which goes from the positive to the negative. There is a fan on one side, there is a vacuum on the other side, so there must be an electric field which goes there. Let me take a contour and let me go on a path which just goes like this. So I start from this point A, I go to point B, and I come back on that. And on this contour, I basically start from A and I come back to A and I calculate my potential difference, which is E dot dl. And that potential difference would be from A to B, E dot dl, plus from B to A, E dot dl. So part of the path I've taken is I'm just putting it parallel to my electric field line arbitrarily, and the other path is going completely through the conductor till I reach point A. Well, electric field on this path is zero, so this integral should be zero, and we are saying that electric field is created here, which is telling me that the potential when I start from A to A should be a positive value. If I assume that there are charges which are present on the surfaces of the cavity, I get into a big problem because I can start from point A, take an arbitrary path, reach back to point A, and I go to a different electrostatic potential, not the potential I started with. And that tells you that because this delta V A to A has to be zero, the electric field between A to B also has to be zero. There cannot be charge which is induced on the conducting surface. So what is going to happen on this cavity is that when I apply my external field, yes, electrons are going to gather here. The positive charges are going to gather in the back side, the furthest back surface. There is no charge on the cavity surface, and electric field inside still has to be zero. This conductor is going to shield this cavity from outside electric field. These are things you see in your daily lives. Your cell phone stops working in an elevator or becomes really poor in an elevator. Right now, we're just doing electrostatics. Put your cell phone in your microwave and dial it. If it rings, it's probably time to change the cell phone. When you have a cavity inside a conductor, if you apply external electric field to that cavity, there is no electric field created inside the cavity. Absolutely no electric field created inside the cavity. That's why if you are stuck in a lightning storm, it is better for you to sit in your car than to walk outside. You would be protected from external electric field inside a car much better than walking outside. This is known as Faraday's cage. As an experiment, you can take a radio and cover it with tinfoil and see whether the radio gets the reception. Try with AM, low frequency, and see whether it gets reception. That is our last rule for what happens when we apply external electric fields to conductors. And let's quickly revise what the rules are. When we apply external fields, E total inside the conductor has to be zero. No ifs or buts about it. In electrostatics, in an ideal conductor which we are considering, E inside the conductor has to be zero. The potential difference between any 2 points inside the conductor has to be zero. Conductors are equipotential. They have the same potential at every single point, whether the point is on the surface or in the volume. There is going to be surface charge which is going to be induced, and the surface charge is going to be negative on one side and a positive on the other side. The total charge remains zero. It is just a redistribution of the charges on the conductor. And there cannot be a volume charge. There is absolutely no way, otherwise you break Gauss law. Volume charge cannot be induced in equilibrium. All the charge which you have induced will go and sit on the surface. Then electric field E has to hit the conductor normally. Electric field will have to bend around in such a way that when it comes and is incident on the conductor, the angle between the electric field and the conductor is always 90 degrees. There is absolutely no parallel component of the electric field on the surface. And finally, conductors shield cavities from external fields. That when you have a cavity inside a conductor, you apply an external field, you are happy inside the conductor, there is no force you are going to face because of that external field. Electric field inside that conductor cavity would be zero. Let's take a few quick conceptual examples to see if we understand things. Let us say I have a conductor, very large conductor, and I put a charge Q inside. If this conductor was not present, so below I have a very large conductor. If this conductor was not present, the electric field from Q, I'm doing it in dotted lines, that would go radially outwards. This electric field is your external electric field. That electric field is going to start inducing charges on your conductor. What is going to happen is you are now going to start getting some negative charges which sit here. Most of the charges are going to try to sit right below your charge Q, And as you go further away from it, the charge density is going to become less. Now what is going to happen to your total electric field? Well, this line will just come and hit 90 degrees. But what is happening to this line? This line wanted to blow up like that. Think of it as a here. It is blowing out, but then there is a vacuum which starts sucking it in. So this line will start to bend, and it would bend in a way that it hits here 90 degrees. Similar to this line, it would bend such that it becomes 90 degrees. The green line is the sum of the electric field due to charge Q, which are the red lines, and the electric fields which are going to be created due to the surface charges on the top conductors. So it is going to basically bend like that on the conductor. Everywhere I go, this has to be 90 degrees. Let's take one more example of how fields would look like. I have charge Q sitting outside, and I have a conducting spherical shell placed next to it. So this is hollow, and the conductor is present here. What would happen? Maybe you want to stop the video, pause the video, draw it out, and then look at the solution and see how well have you matched. All right, here it goes. Assuming again this charge is positive, this is going to create electric field lines which are going to try to radiate out of that charge which is present here. Right? If this charge Q was the only charge, that's how the lines would radiate out. These lines, black lines which I've drawn, act like an external field to the conductor. You are going to start getting electrons which will gather closer to this charge, and as you go further away, the density will decrease, and finally you would have some positive charge density further away. Now, how much of that would happen would depend upon the distance and how strong this charge Q is, but electrons will start gathering on this side, leaving vacancies on the back side. This part is simply the cavity. Electric field inside is simply zero. There is no electric field in that hollow cavity which we have created. How would the electric field line look? Well, this line will go in 90 degrees. This line which wanted to go out now starts getting sucked in by the vacuums there. So this would bend till it hits this at 90 degrees. So if I continue this forward as a tangent, it would go to the origin. Similarly, this lines would bend. Every of these lines would start bending so that when they hit the surface, the angle is 90 degrees. Some of the lines will start to bend, but then they would be repelled by that fan. This fan over here would take over and may actually just leave like that. On the back side, I would have lines again created like that. All these electric field lines would have to be incident on the conductor at 90 degrees. Electric field inside the cavity would remain zero.